multiple bonded compound. First of all, a great salute to all the participants. Really, we wondered when we had that the total number of registrants for the webinar program is more than 1,000 amidst the world across pandemic situation. Thank you, everyone. I'm here to propose my welcome address. It's my honor to welcome the today's chief guest, the respected Dr. Sheela ma'am, Associate Professor of Chemistry, American College, Madurai. This is one of the very good old renowned institution in South India. Thank you so much, ma'am, for accepting our invitation to deliver the topic in the core chemistry.
Yeah, thank you, sir.
Our college as well as our Department of Chemistry feels very happy and proud to welcome you, ma'am.
Yes.
Then I welcome wholeheartedly our beloved head of the department, Dr. Vanangamudi, and all other faculty members of our own department. I am really delighted to welcome all the participants, including faculty members of other colleges and universities, research scholars, and students for this webinar program. Finally, I thank and welcome the organizing secretaries who are the real backbone of this function, Dr. T.veemaraj and Dr. umamaheswari of our own Department of Chemistry, ANJAC College. They have afforded a great effort to conduct this webinar program in a very successful way. I wish them a great success. I thank all of you for this wonderful opportunity given to me. Thank you so much, sir. Thank you.
Thank you, Professor. Thank you, sir, for your valuable speech and welcome. Then I would like to welcome our beloved and respected head of the department, Dr. A. Vanangamudi, sir, Head and Associate Professor of Chemistry, PG, ANJAC College, SIVAKASI, to introducing our today's chief guest, Dr. Dorothy Sheela, Madam. Please, sir. Vanangamudi, sir.
Hello. Hello. Imran?
Yeah, yes, sir. Clear.
Audible?
Yeah, yes, sir. Yes.
Good morning to everybody. First of all, I express my sincere thanks to our beloved correspondent and dynamic principal for giving permission to conduct this webinar. I am very happy to introduce our chief guest, Dr. Dorothy Sheela, Associate Professor and Bursar, Department of Chemistry, American College, Madurai. She did her BSc in Lady College and MSc in American College. She did her PhD in MK University, Madurai. She received CACR Fellowship and Best Woman Associate Professor Award. She has completed one major and one minor research project. She produced 2 PhD and 15 MPhil. She has published 50 papers in international journals and presented 100 papers in the seminar and symposia. With this few words, I hand over the session to our chief guest.
Thank you, sir. Thank you, sir. Thank you for your valuable words and wonderful speech. You are truly speaking about our today's chief guest. Thank you, sir. Now I invite and welcome our today's chief guest, Dr. Dorothy Sheela, Associate Professor and Bursar, Department of Chemistry, the American College, Madurai, to deliver her ideas. Welcome you, madam.
So greetings to all the participants from the American College, and I'm happy to be part of the webinar today. And I thank our Principal and Secretary for his constant encouragement in every act of the college. Now I must wholeheartedly thank Dr. Vanangamudi, the head of the department, and Dr. Kumar Raja for his valuable welcome address. I should appreciate all the efforts that is taken by the organizing secretaries, Dr. umamaheswari and Dr. T.veemaraj for their tireless work. I appreciate you for all the things you have done up to this moment in contacting me repeatedly through mail, WhatsApp and SMS. And thank you, the conveners. And in this webinar, I try to address the third major and the second PG students, especially the third level and fifth level aspiring organometallic chemist. This is mainly focused on the competitive exams and also the bonding concepts and principles. I carefully avoided the equations here because every book is giving equations a lot. You can always read textbook. I have given 7 important textbooks to be referred here. And the last textbook recently released by IIT professors of Gupta and Elias that I have included. And that talks mainly about the basic concept of organometallic chemistry, including the principles and synthetic applications. Of course, the preparation methods are also given. So later you can purchase a book of this kind and then read for your next level of understanding. So mainly the slides will show the bonding concept and the fundamentals of organometallic chemistry that are useful for second PG students and third UG students as well. Now, shall we go to the presentation? Slide number 1.
Madam, please share your screen, madam.
Yes.
Presentation screen.
Yeah, this presentation features the metal-ligand multiple bonded compounds. We all know metal-metal multiple bonded compounds, which are clusters in nature. And these presentations will have metal-ligand multiple bonded compounds having double bonds and triple bonds. And this is the periodic table that shows which type of metals can be involved in that bonding. Here we have transition metal compounds at the middle, and the arrow shows that metal carbon sigma bonds and metal carbon double bonds will be formed by only such class of compounds because they are electron rich. And they have the suitable orbitals for this bonding parameters. So neither the S block nor the P block will be involved here. Only the D block transition metals are largely involved in metal carbon or metal ligand multiple bonded formations. Now coming to the characterization and the spectral analysis, we have several methods here for characterizing the multiple character of the metal ligand bond. And as usual, you have X-ray crystallography, infrared, NMR, mass, elemental analysis. In the others, you can include neutron diffraction studies, where we require large crystals which are always difficult to be obtained because hydrogen atom location is very difficult in X-ray. We need to go to neutron diffraction techniques, and that is to be included here because apart from NMR, we will have good source of data from neutron diffraction. And X-ray will tell about the bond length, infrared will tell about the stretching frequencies, and in NMR we can get coupling constant, in mass we get the fragmentation pattern of the organometallic compounds. And these are the different techniques that are involved in the characterization of metal-ligand multiple bonded compounds. So coming to the first class, I prefer to take Zeise's salt because it was discovered by the scientist called Zeiss in the year of 1827. Even without recognizing that this is an organometallic compound, the scientist died. After 100 years of this discovery, it was designated as an organometallic compound, and the bonding model was given by t.veemaraj, which I will be talking shortly. And when Zeiss took platinic tetrachloride and mixed with ethanol and hydrogen chloride, he could get a beautiful yellow precipitate having the composition PtCl3 eta2C2H4 the whole minus. And this is obtained as a yellow precipitate as a potassium salt. And here, as you see, platinum atom is at the center and it is occupied in a square planar bay. And the 3 corners are occupied by 3 chlorine atoms, and the 4th corner is occupied by the ethylene moiety, where the molecule is perpendicular to the plane of the whole molecule. Now, as you see in the diagram, platinum is bound not to one carbon atom, but it is bound to both the carbon atoms of ethylene. So the X-ray crystallographic data shows that platinum is at equidistance from both the carbon atoms. That means platinum is bound to the center, that is the double bond of ethylene. And platinum as a square planar moiety has underwent dsp2 hybridization here. The bonding of alkene to platinum is further substantiated by the bond length measurements here. As a free molecule, ethylene has C double bond C bond length. After coordination, the bond length is found to be increased. That shows that some part of the electron density is involved in the metal bonding. And this is the metal-ligand multiple bonded compound that was first discovered in the year of 1827. Now coming to the multiple nature here, the metal-ligand bond is a multiple bond. One bond is a sigma bond, the next bond is a pi bond. And the diagram A shows that how a sigma bond can be formed. Diagram B depicts the pi bond formation. Coming to diagram A, it shows ethylene molecule is having a filled p orbital, and that filled electrons are now given to empty dsp2 hybrid orbital of platinum in order to form a sigma bond, otherwise it is a coordinate bond. Coming to the second bond, it is a pi bond, otherwise a back bond. First bond is a sigma bond and a coordinate bond, and the second bond is a pi bond and a back bond. And this is done by the overlapping of filled dxy or dxz orbital of metal with empty antibonding pi star orbital of ethylene. Now as the diagram shows, the metal orbitals are filled, so they are shaded, and the pi star orbitals of ethylene are unshaded, showing that they are empty. So first bond is a sigma bond and the second bond happens to be a pi bond here. Because suitable orbitals and suitable energy and matching are there, such types of bondings are available here. Now coming to the structure of square planar complexes, this you can get it even from coordination chemistry easily. And there are 16 electrons in this compound, and this obeys 16 electron rule, being the platinum metal coming along with nickel triad. And the bracketed thing shows that the 4 electron pairs that are obtained from the metal. And this is another diagram where it shows the 4 electron pairs that they are obtained from the ligand. So totally 8 plus 8, 16. And this diagram shows the highest level dx square minus y square orbital, which is not occupied. All the rest of the below orbitals are occupied with 16 electrons. So the molecule is happy containing 16, not 18. Because the further occupation of the antibonding like orbital dx square minus y square will lead to the instability of the whole molecule, being it is antibonding. So the last orbital is left free because it is having a very high energy in the case of D8 square planar complexes. So Z salt obeys 16 electron rule, having this completely filled configuration up to the bonding level, carefully avoiding the antibonding x square minus y square orbital. And that tells the stability of the molecule. And we shall here have the concept called as concept of unprolonged. Unprolonged is a German word. The meaning of the word is reversal of polarity. The slide discusses about the reversal of character of alkenes. As a free molecule, alkenes are electron richer. They will not undergo nucleophilic substitution reaction because the electron density is high. But upon coordination with the metal, it yields some amount of electron density to the metal, and it becomes electron deficient in nature, and due to electron depletion of electron density, it can now be attacked by a nucleophile. And this is the example that is given where iron is attached to an alkene. Alkene gives electron density to iron and becomes electron less denser. Now it can be attacked by a nucleophile and we get the resulting product. And this reversal of polarity is called as Umamaheswari, and the meaning is reversal of polarity in German. And this we can have it as an example of remarked changes of the coordinated ligands. Otherwise we call it as drastic changes in the behavior of alkenes upon coordination. And this change is highly dramatic. Once it was not a nucleophilic way attack reagent, but after coordination, a nucleophile can come and easily attack. And this we call it as drastic changes in the coordination behavior of alkene ligands. Otherwise, it is called as reversal of polarity or Umamaheswari. And next class of compounds are metal carbonyls, and this you know it even from UG level. And this we have the synergetic effect, where a sigma bond and pi bond are formed as usual in the case of alkenes. And this we call it a synergism because the sigma bond strengthens the pi bond and the pi bond strengthens the sigma bond. That is vice versa. The formation of the sigma bond accumulates electron density on the metal, and it helps the metal to dissipate the electron density once back to the ligand to form the pi bond. So the formation of the sigma bond facilitates the formation of the pi bond. And because the pi bond is formed, the carbon monoxide now becomes electron denser. Otherwise, it is a weak Lewis acid ligand which cannot donate the electron density easily. Because of formation of the pi bond, the CO, which is a small or otherwise weak Lewis acid, is made to behave as a better Lewis acid. So the formation of the pi bond strengthens the sigma donation of CO. So one is helping the other. Sigma is helping pi and pi is helping sigma. And this is called as a synergism. And this diagram shows the formation of the pi bond. And you all know sigma bond is formed by the donation of pair of electrons from the sp hybrid orbital of CO to the empty hybrid orbital of the metal. And this orbital diagram tells you the filled dxz orbital of the metal being donating electron density to the empty pi star antibonding orbital of CO. Though antibonding, the energy conditions are matching, so the homo-lumo pairs are in a matching way. Donation and occupation is highly possible in CO complexes. Otherwise, metal CO complexes may not be stable because of multiple bonded characterization of NC. They are stable, having the melting points in the higher range. The stability is because of multiple nature of MCO bonding. And this diagram is for pi bond formation of MCO. And this is the slide that is representing the resonating structure of MCO linkages. So originally M single bond, C triple bond O. There is an electromeric shift from metal to carbon, and we have the second resonating structure B. So on going from A to B, the MC single bond is becoming MC double bond, whereas the CO triple bond is becoming CO double bond. So original single bond is becoming a double bond, original triple bond is becoming a double bond. That means, according to resonating structure B, the bond strength of MC increases while the bond strength of CO decreases. So there is an increase in MC bond order and there is a decrease in CO bond order. As it was told in the third slide, infrared spectral data are highly useful in understanding the MC back bonding or multiple nature. So we can give only 100 rupees for recording the infrared spectra and get very good information about the back bonding involved in metal carbonates. Rather than going to X-ray crystallography, which is very costly, we can have a glimpse of the multiple bond even from the Ayya spectral data. So when resonating structure B dominates there will be an increase in MC stretching frequency and decrease in CO stretching frequency compared to free CO. And this is the usual data that we always encounter. And you have positively charged, negatively charged and neutral species listed on the left side. And the corresponding Ayya stretching frequency of CO are also listed. See, as you see here, and this is the back bonding from A to B, when the charge of the metal ion is more negative or when the metal ion is more electron denser, the degree of back donation will be more. So the contribution of resonating structure B will be more, and you will have high bond order of MC and low bond order of CO. If the bond order is low, the stretching frequency will be also low according to Hooke's rule. So when the resonating structure B is in dominant in the resonant hybrid, we will understand that higher the electron density on the metal, higher will be the degree of back donation and lower will be the bond order of CO and lower will be the stretching frequency of CO. And this isoelectronic series also tells the same. there is a beautiful correlation between the charge over the metal ion or the whole compound and the CO stretching frequency. The last compound has two negative charges. That means titanium is more electron rich. So the degree of back donation is more. So MC bond will be becoming a double bond and CO bond will be reduced from a triple bond to double bond character. And so there is a large reduction in CO stretching frequency in the last compound compared to compound 1. So we understand as the degree of back donation increases, the contribution of structure B increases, and there is a corresponding increase in MC stretching frequency and a decrease in CO stretching frequency. Right. Now here I have given the bonding of hydrocarbon, which is again ethylene or any alkene to the Wilkinson's catalyst, and the bonding model is the same. And we encounter several catalytic reactions using alkenes here. And one such example here is a Wilkinson catalyst where we have ethylene bound to rhodium and which is converted into alkane. And here I wanted to include the hydrogen addition also, because the hydrogen addition is exactly the opposite way as that of CO. The bonding situations are opposite and it breaks the molecule into two portions. See, for example, if you take hydrogen, dihydrogen, H-H, the bonding electron density is donated to the metal to form the sigma bond. And at the same time, the metal back donates its electron density to hydrogen. And in this case, the back donated electron density is accepted in the sigma star orbital of H2, not the pi star orbital as in the case of CO. As you know, the sigma star orbitals are highly antibonding in nature, and any occupation in the antibonding orbital will lead to reduction in the bond order. If the electronic deployment is so much high, H2 will be broken into dihydride molecule. So dihydrogen will be broken into the hydrido molecule. So that depends on the draining of electron density from the metal. If large amount of electron density is accommodated in the sigma star of hydrogen, it breaks the hydrogen molecule into the hydrido complex. And this is much useful in many synthetic pathways of organometallic way cycles. And here also we come across alkenes metathesis. For this, the latest Nobel Prize went to Schrock for his invention of Schrock carbenes. So 2005 Nobel Prize was given for organometallic developments, where several industrial processes like ring opening metathesis, ring closing metathesis, and several other scopes are there, which were beautifully given by Shriver and Atkins. The latest edition of Shriver, edition number 4, talks more about alkene metathesis reaction, which are all missing in some of the books. So metathesis means it is double displacement. Alkene metathesis means the double bond is displaced. Displacement of double bond occurs here in a normal way. And now the second generation catalysts are made here using NHC. NHC analogues, which are very much soluble in all the reaction conditions, and we can use varieties of compounds here without any polarity reasons or for steric reasons. So second generation alkene metathesis reaction is now carried out by N heterocyclic carbons, and this is the simple mechanism. The compound number 1 is the Schrock carbene, where metal and carbon are multiple bonded with a double bond. And the second compound is a substrate, which is your alkene, and the substituents are C, D, E, F. Now they give an intermediate where the metal is now bound to the alkene. And there is a slight rearrangement reaction, and that involves the formation of metallocyclobutane. So there is a cyclobutane ring with metal at one corner. Then there is a shifting reaction taking place, and we get now metal connected with the carbon with EF moieties. Originally, the carbon contained AB in the starting material, and in the final, you have E and F attached to the carbon. The original alkene contains CDEF. Now the product alkane contains ABCD. And this is what is called as alkene metathesis, which can happen under normal conditions using the carbene analysis. Now they are industrially important for several polymerization reaction. It may be opening or it may be closing or it may be cross, where metathesis reaction take place and we get several important products from this mechanism. And that is why the Nobel Prize went to Schrock for his invention of Schrock carbene. And this is the table that shows single bond, double bond and triple bonded compounds that we come across in organometallic chemistry, where here we will have carbenes and carbynes be done little later. And we will go to carbenes now. So carbenes are carbon metal double bonded compounds. There is a direct double bond between metal and carbon. So metal is directly attached to carbon atom by a double bond. And this was invented by Fischer in the year of 1964. And carbenes, as you know, are Cr2 and there is a pair of electrons. They are very reactive. And there are two types of carbenes, as you know, starting from your first year lesson, singlet carbene and triplet carbene. Singlet carbenes have sp2 hybridization and triplet carbenes will have sp hybridized carbon. And the pairs of electrons are, because it is singlet, one upspin and one downspin, triplet both are upspin. So two types of carbenes we come across. And Fischer carbenes have singlet carbenes, and there is another scientist called Schrock, and he has discovered another type of carbenes which contain triplet carbene moieties. So singlet and triplet. And these are the carbene complexes, Fischer and Schrock. And here in this slide, I have tried to differentiate between the Fischer type of carbene and Schrock type of carbene. And number one characteristic, metal and oxidation state. Fischer types of carbenes are formed by the middle transition metals, whereas the Schrock type are formed by early transition metals. Coming to the oxidation state, Fischer type, low oxidation state, always 0. Schrock type, high oxidation state, titanium 4+ and tantalum 5+. Then coming to the characteristic nature of the substituents that are attached to carbene carbon. In the Fischer type, the carbene carbon moieties are highly electronegative like OMe, or it is containing nitrogen or sulfur as the joining atom. They are electron donating in nature. They are pi donating in nature. Coming to Schrock type of carbene, they are not pi donating. Coming to the electron count, Fischer type 18, always obeying the 18 electron configuration, and Schrock type, they may vary from 10 to 18. Now coming to they do not obey the 18 electron rule perfectly all the time. Coming to the bonding feature of Fischer carbene, and this is the Fischer carbene moiety. There are 4 orbitals in carbon, and one orbital is having the pair of electrons, which is the sp2 hybrid orbital. So it is a singlet carbene. One pz orbital is left empty, and the other one are bound to OR and R. sp2 hybrid orbitals are 3 in number. One is bound to alkoxy group, another one is bound to R, and another one houses the pairs of electrons. Then the pz is empty. So what is happening here is the sp2 hybrid orbital, which is housing the pair of electrons, is donated to the metal to form the sigma bond. Then metal back donates electron density, which is now accepted by the empty pz orbital of the carbene. And that is how the bonding is finished. And here you see metal double bond C, because carbene is giving a pair of electrons to the metal, and we get a sigma bond, and the pi bond is by the back donation. So our molecular structure becomes M double bond C, single bond OR and single bond R. Now there is a resonance between two types of structures A and B, because the ligand on the carbene carbon, which is OR, oxygen has also pairs of electron that can also be donated to carbon. So I can have another structure possible here by the donation of electron density from alkoxide moiety, and we have C double bond O also. And the below diagram shows the orbital overlaps here. The metal D electrons are now transferred to carbon to form first type of resonating structure. And the second structure, oxygen is donating electrons to carbon, and so we are having double bonded structure. But the spectroscopic data shows that resonating structure B is dominating. But anyway, the metal carbon bond order is in between 1 and 2. It is more than a single bond, but lesser than a double bond. So the bond length measurement and the bond order measurements are telling that the bond is in between a single bond and double bond. It is definitely greater than 1, but it is less than 2, because both type of resonating structures are prevailing. That depends on the nature of substituents along the metal. And this is the reaction that shows the carbene carbon on Fischer carbene is electrophilic in nature. Because it is an electrophilic in nature, ammonia can be now added. Ammonia is a nucleophile having the lone pair, and that can be now added to carbon to get the final product. So this chemical reaction tells us that the carbene carbon in the Fischer carbene is electrophilic in nature. And this is the slide that is consolidating the characteristic feature of a Fischer carbene. Here it is listed. If you are asked to select whether the carbene is a Fischer or a Schrock carbene, you can use these rules to differentiate Fischer from Schrock. Coming to Fischer carbenes, the characteristic features listed are, this is from QE, metals are in low oxidation state, that is 0. The auxiliary ligands, the ligands on the metal, they are pi accepting because they are carbon monoxide ligands usually. Now coming to the ligands that are present in carbene carbon, they should be pi donating. And the carbene carbon, as I said in the last slide, they are electrophilic in nature. They are usually electrophilic in nature as illustrated by the chemical equation in the previous slide. So there are 4 important features of a Fischer carbene. Metal should be in the low oxidation state. Auxiliary ligands on the metal are pi accepting. Ligands on carbene carbon are pi donating. And the carbene carbon is electrophilic in nature. The equation shows one of the preparation method for the preparation of Fischer carbene. So the last equation, CO5 times M double bond C OMeH. So this is a typical Fischer carbene. What are the characteristic features? The oxidation state of metal is 0. The metal may be tungsten or molybdenum or chromium. Metal oxidation state is 0 because the starting compound is MCO6. Here also it is MCO5. So there is no change in the oxidation state. Metal is in low oxidation state, 0. Coming to the auxiliary ligand, the auxiliary ligands are carbon monoxide which are highly pi accepting. So condition number 2 is also okay. Condition number 3, ligands on carbene carbon are pi donating. The carbene ligands are OMe. There is oxygen present. It may be oxygen, nitrogen or sulfur because oxygen is sitting over carbene, which is pi donating. Condition 3 is also obeyed. So condition 4, the carbene carbon should be electrophilic, and that is illustrated by the appropriate chemical equation. So you should have all the above 3 conditions satisfied in order to label a compound as a Fischer carbene. Coming to Schrock carbene, and this is the method of preparation of a Schrock carbene. In the starting material, you have tantalum alkyl chloride complex, where the oxidation state will be +5. There are 3 alkyl ligands and 2 chloro moieties. So tantalum has the maximum oxidation state of +5. So coming to the features here, the exactly opposite conditions prevail between Fischer and Schrock. Here we are telling metals in high oxidation state, and the auxiliary ligands are non-pi accepting, and the ligands on carbene carbon are non-pi donating, and the carbene carbon is nucleophilic in nature. So you see the carbene here, The last compound is the sharp carbene in the equation. See, the metal ion is tantalum. The oxidation state is +5. So high oxidation state. Coming to the auxiliary ligands, it is only an alkyl ligand. It cannot act as a pi accepting ligand. They do not have the pi accepting character. So the auxiliary ligands are not pi accepting. Coming to ligands on carbene carbon, they are not pi donating because they are only hydrogen and alkyl group. Then coming to the last point, carbene carbon is nucleophilic. And the nucleophilic nature is illustrated by the reaction with aluminum trimethyl. And as you know, aluminum trimethyl is an electron deficient molecule having only 6 electrons. And it will seek for another 2 electrons to get the octet completed. So if it is having a chance to react with an electron rich molecule, it will be attaching here very nicely. So because the carbene carbon is nucleophilic in nature, it can be attached with aluminum trimethyl and forms an adduct like this. So this chemical equation shows that carbene carbon is nucleophilic. And we said earlier, Schrock carbene is a triplet carbene. And this is the triplet diagram. Again, the hybridization is sp2. But one of the hybrid orbital is housing only one electron, not a pair of electron. And another orbital has gone to the pz orbital. And this is the opposite way of filling. In the earlier Fischer carbene, we said a pair of electrons are housed in sp2, whereas pz was empty. But here the situation is different. One electron is in sp2 hybrid orbital and another electron is in the pz orbital of carbene. Now coming to the bonding here, the metal is having one electron that is combining with another electron with carbene to form a sigma bond. And then other 2 electrons will overlap inside way to form the pi bond. And this is the qualitative molecular orbital diagram that shows the electrophilic and nucleophilic relation, nicely picked out from Shriver and Atkins. Coming to diagram A. Diagram A represents Fischer carbene. Where you look, carbene carbon has a very high energy. And this is only a qualitative molecular orbital diagram, not quantitative. When these atomic orbitals and the group orbitals overlap, you will get at the center molecular orbitals. You see this molecular orbital contains a pair of electrons which is away from carbon and close to the metal. Because the electron density is away from carbon, the carbene carbon becomes positively charged or it is electrophilic in nature. So it can react with the nucleophile. Coming to B, it is of Schrock carbene. Schrock carbene carbons are lower in energy. So they are now closer to the bonding molecular orbitals. And so they are electron richer here. So in the first part of the diagram, electrons are away from carbon in the bonding molecular orbital. So carbon becomes electrophilic in nature. In the second set of carbenes, the bonding orbitals are closer to carbene carbon. So carbon is electron rich or it is nucleophilic. And this tells you why the reactivities differ because of electron charge density. Densities are differing according to the MOs here qualitatively. And we shall go to carbynes here, and this reaction is interesting. Carbenes are M double bond C. Carbynes are M triple bond C. And nobody was expecting carbynes would appear in the organometallic chemistry. The scientists wanted to brominate a Fischer carbene with BBr3 initially. They wanted to get a bromo derivative, but they could not get the bromo derivative form. Instead, a new product appeared in the reaction vessel, which was identified as metal carbynes. So, similar to carbenes, we may have carbynes also, where the metal is directly bonded to carbon with a triple bond. So, the discovery is highly accidental. Nobody meant for that. But we could now see there is a triple bonded metal compounds also present in organometallic chemistry. And coming to the bonding features will be coming in the transparencies later. Now metal alkynes. Carbenes are over, carbynes are over. Now we will go to metal alkynes, which are similar to metal alkenes like zisol we have discussed earlier. And alkynes are triple bonded compounds. They potentially have 2 pi bonds, so they can act as a 2 electron donor or as a 4 electron donor. And these are the possible modes of alkynes which can be bound to the metal. And coming to the carbene, or it is carbine. Carbynes are 3 electron donors similar to NO. NO is a 3 electron donating molecule. A pair of electron from nitrogen and 1 electron from the 2 pi pz orbit, py orbital of NO will be donated. And here in the triple bonded compounds, you have the carbine moiety, which is the sp hybrid one housing the pair of electron donated to the metal to form the sigma bond. And then there is 1 electron in the pz orbital, which can be combined with an odd electron in M to form a first pi bond. And the second pi bond will be formed by the back donation. And this is the bonding in carbine. Bonding in carbine moiety. The slide 32 should go along with 30, and it has somehow, I got it misplaced. And this is the bonding in the case of metal carbynes. And we shall go to some of the different modes of bonding in alkynes. And the molecule is platinum, BH3 thrice, and some alkyne moiety is attached. And there are several modes, as I said. And now this mode is called as a double sigma bond model, where platinum is added across a double bond. Only one double bond is utilized here. And this is illustrated by the bond length measurements and infrared spectroscopy, where the bond length is equal to 1.32, which is similar to that of C double bond C in chemistry. And C double bond C stretching frequency usually comes in the range of double bonded range, 1700 centimeter minus 1. These two, spectroscopic and the bond length NADAR, suggest that this is the model of alkyne that is bound to platinum. They all obey the 18 electron configuration. Now this is another mode where only one single bond is attached to platinum, and the CC bond length is similar to that of a triple bond, 1.24. This molecule also obeys 18 electron rule, as you could see. And there is another mode called as the last mode, CO2CO8 plus R2C2R2. When this molecule is reacting, 2 carbon monoxide molecules will be liberated. So the scientists were wondering, if 2 CO are left out, 4 electrons should be now compensated. Then they could understand that the acetylene molecule is giving 4 electrons for bonding. Because 2 COs are displaced, in the place of 2 COs, 2 double bonds should occupy there for bonding features. And the interesting thing here is, both the double bonds are mutually perpendicular to each other, so they cannot be bound to cobalt metal ion directly. So the cobalt has to bend over in order to get a good overlap of 2 of the pi bonds here. As a result, the molecule takes a tetrahedral structure with carbon atoms having sp3 hybridization. And the triple bond is now becoming a single bond, having donated both the pi bonds of electrons for bonding. And this is illustrated, or it is evident from the spectroscopic data, where the C single bond C of the complex is observed around 1403 centimeter minus 1. So the molecule is bending in such a way that the both pi bonds are involved in bonding. So these are some of the 3 different modes of bonding of alkyne complexes. Now I have a slide for dinitrogen compounds also, where dinitrogen complexes are similar to CO. CO is isoelectronic with N2, both have 10 valence electrons. But there are 2 major differences between CO and N2. And the first one is lack of polarity of nitrogen. And the second one is the inability of nitrogen to behave as a pi acceptor. Though it has empty LUMO pi star orbital, the pi star orbital of dinitrogen is of very high energy. So the electrons coming from metal cannot be accommodated in the pi star orbital. Though availability of orbital is there, there is energy mismatch, so it can never be acting as a pi acceptor similar to carbon monoxide. But carbon monoxide is also polar in nature, carbon and oxygen, but nitrogen is a non-polar molecule completely. And one example that has the X-ray crystallographic data available is cobalt PPH3 thrice N2H. And the structure of the molecule is here. Here is also back bonding. Nitrogen is a triple bond, and that is bound to cobalt. So the bond order is reduced from 3 to 2.5, the data says. At the same time, there is back bonding from the metal to nitrogen. So the cobalt nitrogen bond is shortened compared to other cobalt nitrogen bonds in coordination chemistry. So there is a sigma bond formation. There is also a pi bond formation in the case of dinitrogen compound. And here we have the complexes of nitric oxide. Nitric oxide is also called as nitrosyl, NO. And NO is also similar to CO, except that there is one electron extra present in NO. In CO, there are 10 electrons. In NO, there are 11 electrons. And the 11th electron occupies the antibonding 2p pi star orbital. Here there are two potential sites of binding, N and O, but N preferentially binds avoiding the positive charge or the electronegative atom, which is oxygen. So there are two types of nitric oxide bonding. One is linear, 3 electron donating capacity. Another one is bent, 1 electron donating capacity. And the diagram shows the 11 electrons that are accommodated in NO molecule. There is an odd electron here. So this species is always EPR active, and many of the anti-cancer studies make use of NO. Right. Now coming to nitric oxide preparatory work, it is always very difficult to prepare the nitric oxide complexes because they make use of concentrated nitric acid, which is highly oxidizing, and it will break the molecule open, and no complete reactions are possible with pure nitrosyl. So always you will have mixed ligand complexes here. Some ligands may be CO and some may be NO, like that. Pure nitrosyls are very difficult to be obtained because of stringent experimental conditions that are involved here. Now I said there are two types of bonding, linear and bent. Linear 3 electron, bent 1 electron. Whether it is linear or bent, they depend on the nature of the metal ion. Suppose if the metal is an electron poor metal, it can accept the pair of electrons from nitrogen happily, and NO will be remaining as an sp linear configuration. If the metal is electron rich, because it is already electron denser, it will accept only 1 electron from nitrogen, and the pair of electrons are pushed back to nitrogen. And this allows NO to take the sp2 bent configuration. So when the metal is electron poor, we will have linear nitrosyls formed. When the metal is electron rich, bent configurations are always preferred. So the molecule can change the linear configuration to bent depending on the stereochemical valence or the requirement of 18 electron rule, etc. But generally, the electron poor system will have linear arrangement of NO, and electron rich system will have bent. And mainly we come across the linear nitrosyls, which are 3 electron donors. Why they are 3 electron? A pair of electron from nitrogen, and the odd electron is also given for bonding. And this is again a series of compounds formed by nitrosyls. As you see, they are mixed ligand compounds with 5 cyanides and only 1 nitrosyl sitting. So from top to bottom, the negative charges are increasing. So that means the pi back donation from the metal to nitrosyl will be increasing, and N triple bond O will become N double bond O. So the corresponding stretching frequencies will also differ. In the first compound, it is similar to the triple bonded range, 1944. In the second compound, slowly coming to the double bond range. In the third compound, it is slowly decreasing to 1600. So higher the negative charge, higher will be the back donation, and lower will be the NO stretching frequency. In the free NO, it was given 2000 centimeter minus 1. So correspondingly, the stretching frequencies are decreasing, showing the back bonding that is involved in nitrosyl compounds also. And here is an interesting point on brown rings test. And we are familiar with the test starting from our +1. We used to test for nitrates, and this is the confirmatory test for nitrate anion, where we take the given solution and add freshly prepared ferrous sulfate, and slowly we add concentrated nitric acid along the sides of the test tube. If a brown ring develops, we say nitrate anion is given in the sample. We write the given sample or the given salt contains nitrate anion. And this is the brown ring test that has the composition of FeNO H2O5 times 2+. So here you come across a nitrosyl compound. And this is a gate question, one time asked in the gate exam, about the paramagnetic character of the compound. The answer is iron is in the oxidation state of +1, and it's a D7 configuration. The majority of ligands are water, so they are weak field ligand. So you will have the high spin arrangement that will lead to the number of electrons is equal to 3. So corresponding Bohr magneton value will be something around 3.74, like that. Here nitrosyl is a positively charged ligand because one electron will be lost in bonding, and it should be considered as a positive charge when you calculate the oxidation state of the metal ion. See, in coordination chemistry, we have only few positively charged ligands coming. Nitronium ion and then hydrosonium ion. And this is nitrosyl, should be taken as a positive charge. When you go and calculate, it will be giving iron atom in the +1 oxidation state. The compound is not very stable. This will be simply disappearing in few seconds. But the magnetic moment was found to be 3 point something, and the number of unpaired electrons are 2. And so 3. And this is a diagram given in QE about the NO bonding. So metal is bound to NO, and there is a sigma bond and there is a back bond. And there is a beautiful illustration of what is called as stereochemical valence. See, in the compound number 1, it is a linear nitrosyl. In compound 2, it becomes a bent nitrosyl. Compound 1 is 2+, cobalt 2+, which is electron poor system. So nitrosyl takes the linear fashion, allowing sp hybridization, and a very good back bonding is possible here because it is linear. Upon coordination with SCN-, it needs to take the bent bond here. Nitrosyl become bends, and then it is in one electron donor. See, the molecule is beautifully accommodating itself so that 18 electron rule is obeyed here. See, the initial molecule, it is an 18 electron compound. Cobalt is 9, and there is a diazine ligand, so 8 electron 17, and NO will be 3 electron donor 20, and the overall charge is 2+, and this is an 18 electron compound. When it is coordinated with SCN-, in order to allow room for the thiocyanate ion entering, the linear NO will be taking the bent form, and now bent NO will donate 1 electron for bonding, and SCN- will be giving 2 electrons, and the overall charge is plus. Again, the molecule behaves in an 18 electron fashion. So in order to accommodate the incoming ligand, the NO takes the bent fashion, that is the pair of electrons. There are 3 electrons donated earlier. Now the cobalt atom pushes back 2 electrons to NO and takes up only 1 electron, so that NO is allowing to sp2 hybridization, and it becomes bent 1 electron donor. And this phenomenon is called as stereochemical control of valence, discussed in QE. And now I have made references from these books, mainly QE, and Porterfield gives beautiful examples, and Cotton and Wilkinson is good for studying petality cycles. Powell gives more examples in principal organic in the carbonyl compounds, and Purcell and Coates also gives dramatic changes in the coordination behavior. William Jolly gives very nice examples of reactions in 18 electron rule, and the last book, Gupta and Elias, basic organometallic chemistry gives also the principles. All the books will be useful. One or other book will be having some classical examples, so you can have the mixture of books to have a good outlook of organometallic chemistry. Now I have put few slides of question and answer that were taken from CSIR UGC pattern, and you can have a screenshot or you can have the transparency from your convenience and try to make the questions to be answered when you are free. So all will be 21, up to 21 questions are here for you to answer and to ponder. And now with this, I will complete my presentation. I think I have largely taken 1 hour for the presentation, and thank you so much once again for the management of ANJAC College and the conveners and the coordinators for your invitation. I hope the slides were useful and simple for you. So looking forward for your questions.
Thank you, ma'am. Thank you.
Thank you, ma'am.
Thank you, ma'am. Was it audible and clear?
Yes.
Yes, madam. Thank you, madam.
Okay. Well,
Thank you for your valuable words and a wonderful speech. It's truly speaking, it is very useful for us.
Okay, sir. Okay.
Thank you, ma'am.
Thank you.
Yes, madam. It is really inspiring us. Thank you, madam.
Hope that some of the things are covered.
Yes,
Yes, madam.
Okay, ma'am.
Now invite all the participants to interact with our chief guest. Also, participants post your questions in that chat box also. Those who are directly interact with our chief guest, please kindly unmute your audio and video. Please interact with our chief guest.
Dear participants, if you have any questions, you can put it in the chat box. It will be answered by the resource person.
Shabnam, questions post பண்ணுவாங்க. Sorry.
Hello, ma'am.
Yes, ma'am.
Ma'am, I'm Janani from Madras Christian College. I have one doubt.
Okay.
Even though we have a metal carbonyl bond in vitamin B12, that is cyano complex, why we are not considering that into organometallic complex?
Ma'am, can you please louder? It's not audible, ma'am.
Metal cyano complexes are considered to be, that is in vitamin B12, are said to be natural organometallic compound. Hello?
Hello, I am not clear about your voice, ma'am. Please be audible.
Ma'am, I'll post it in chat box.
Okay.
Okay. Thank you, ma'am. Thank you.
Ma'am, one more question was asked by Kaviraj. Compare Fisher and stock carbine. Which one is more reactive?
Shark are more reactive.
Shock.
Because they do not obey the 18 electron configuration, they cannot be stable. And that is why alkyne metathesis reactions are carried out with shark carbines. The instability promotes reactivity, and the Nobel Prize went to Schrock because of this invention. Because they do not obey the configuration perfectly, always varying from 10 to 10 electrons. Schrock are very reactive, but Fisher are very stable.
Ma'am, one more question. Yeah, okay, thank you, ma'am. One more question was asked by our participant. Metal cyano complexes have metal carbon bonds and still not considered as an organometallic compound. And Wilkinson's catalysts have no metal carbon bond and they are classified under organometallic compounds. Why?
Ma'am, can you repeat the question, ma'am? Because we are not able to hear that.
Okay, ma'am. Okay. This question was asked by Shanmuganathan. Metal cyano complexes have metal carbon bonds, but still they are not considered as an organometallic compound. And Wilkinson's catalysts have no metal carbon bond and they are classified under organometallic compounds. Why?
The Wilkinson's catalyst, after binding with alkene, it becomes organometallics. Is it okay? But it contains PPH3 ligand, which is a main group organometallic compound because it is a phosphorus containing ligand. And this donates electron pair and accepts the electron pair also. And the whole cycle involves a metal alkene complex preparation, so it is included in organometallic chemistry. And PPH3 is considered to be a main group organometallics, not transition metal organometallics. Phosphorus belongs to the P block in the periodic table, so PPH3 is a P group organometallic compound, not D block. And that is why it's coming. Any more clarifications?
Okay, thank you, ma'am. Ma'am, one more question. You said why Fischer carbene is very slow reactive than shock carbene. Why? What is the reason?
Fischer carbenes are 18 electron components which are very stable. All the available molecular orbitals are filled. 6 bonding orbitals and 3 non-bonding orbitals are fully occupied. That means they have stable 18 electron configuration. They will be reluctant to act. Whereas in the case of Schraff, they are less than what is required for 18 electron magic number. They range from 10 to 18. They are always electron richer, lesser. So they are bound to react in a higher way. The electronic configuration is the reason.
Okay, ma'am. Thank you. Ma'am, one more question was asked by Subha. Can polymeric materials be used as organic ligands?
Yes, they can be used depending on their binding properties. That depends on several factors: the oxidation state, the electron count, the size of the metal ion. Everything is there.
Okay, okay.
Any more clarifications?
Yes, thank you, madam. Thank you all the participants and our chief guest for this wonderful interactive sessions. Now I invite Dr. S. Umamaheswari, Assistant Professor of Chemistry, ANJAC College, to propose vote of thanks. Madam, welcome.
Okay. Good afternoon to one and all present here. First and foremost, I would like to thank God Almighty for the successful completion of this webinar. I wish to express my heartfelt thanks to our today's resource person, Dr. Dorothy Sheela ma'am. I know well that Madam is a very busy person. In spite of her busy schedule, Madam has accepted our invitation and shared her magnanimous knowledge with us today. Starting from zinc salts, Madam has explained various organometallic complexes such as metal carbonyls, metal nitrosyls, metal carbynes, etc. Madam has clearly explained various bonding mechanisms, and especially it's very useful for those who are preparing for competitive exams in chemistry. Definitely, this program might enlighten the minds of all. Thank you very much, ma'am, for your valuable presentation. Thank you. Thank you, ma'am.
Thank you, madam. Thank you, madam, for your valuable speech.
At this moment, I would like to thank Dr. Dharmaraj sir for his help in organizing this program. Thank you, sir. Thank you.
Thank you, madam. Thank you all the participants and madam, Dr. Sheela madam.
I would like to, sir, wait. I would like to extend my heartfelt thanks to our beloved principal sir and the college management for giving consent to conduct the webinar. I express my sincere thanks to Dr. Vanangamudi sir, Head Department of PG, and Dr. Kumaraja sir, Head Department of UG, for their guidance and support. I am very happy to thank Dr. Veemaraj sir for his support in organizing this webinar. My deep sense of gratitude goes to all the learned and dedicated staff members of our department. I would like to propose hearty thanks to Dr. Venkatesh sir for his technical support. I extend my thanks to our student volunteers, Mr. Chalapandian from 2nd MSc Chemistry and Mr. Sivashankar from 3rd BSc Chemistry. I extend my warm thanks to my dear friends from various colleges for their huge support in sharing the webinar invitation through social media such as WhatsApp and Facebook group, etc. My grateful thanks to all the participants for the support, cooperation, and spending your valuable time with us. Thank you, one and all. Thank you.
Thank you, madam. Thank you, madam. Thank you for your.
Thank you, Vikraj. Thank you.
Yes, thank you,
ma'am. Thank you.
Thank you.
Now end of session. I request all the participants, please kindly fill the feedback which is available in the chat box itself. You can follow it in YouTube also. So please fill up feedback. Thank you all your support for your constant participation. Thank you. Your e-certificate will be sent to your registered email ID soon. Thank you. Thank you, everyone. Thank you, madam. Thank you, madam.
Thank you, Pa.